Alright, let's go ahead and get started with Lesson 7, Matter. To do this lesson video, it might be recommended that you use your periodic table to refer to it from time to time. Alright, so we're going to first start out with a definition of what matter is. And it simply is anything that has mass and takes up space. So we can look at matter as having mass and volume, since the definition of volume is the space an object takes up. Alright, we're going to classify matter. Matter can be broken down into two different things, or two different categories: pure substances and mixtures. So we can connect these like so, broken down into a mixture and pure substances. Pure substances are either elements or compounds. So they're broken down into elements and compounds. Mixtures, there are two types of mixtures. There are homogeneous and heterogeneous mixtures, and we're going to look at all of these components. So you need to know the classification of matter, this diagram here that we have. Again, matter is broken down into pure substances and mixtures, and pure substances are elements and compounds, and mixtures are either homogeneous or heterogeneous. Alright, so let's define element. We know that an element is a pure substance of matter. But what exactly is it? Well, right now we're going to keep it pretty simple. We'll get into some more specifics of what elements are later on. But for now, it is simply, let's say, elements are considered the building blocks of all matter and material. What does building blocks do? Well, building blocks make things. They are structures to things. And so elements, that's exactly what we do. We take elements and put them together, and we make structures and make things. So all matter in the universe and on Earth is built out of elements. So an element is a unique form of matter that can exist on its own or in a combination with other elements. And this is a really important point, and that is elements cannot be broken apart into two different substances by chemical reactions. That last statement there, you should highlight, star, make note of. It's very important. I will quiz you on that idea. Alright, so if you look at your periodic table, you will see that there are 118 known elements, but only 92 of them are naturally occurring. The rest are all man-made. All matter in the universe is either an element or is made up of some combination of these elements. So, as far as the natural occurring ones, if you look at your periodic table, and you'll see element number 1 is hydrogen, element number 2 is helium, and all the way down to element 92, which is uranium. Uranium, number 92, is the last naturally occurring element. After that, going to 93 on, those are all man-made elements. Alright, each element has a specific name, like silver or potassium or Einsteinium, and it has a chemical symbol associated with that name. The symbol for elements consists of an uppercase letter, which are sometimes followed by lowercase letters. If you look at your periodic table, you'll see that all the way through, the first letter is always uppercased or capitalized, and if there is a second letter, it is lowercased. Here's some examples. Silver, for instance, has a symbol of Ag, capital A, lowercase g. Potassium is just a capital K, and Einsteinium is ES. Now you might look and say, well, silver has a symbol of Ag, and there's not even an A or a G in there. And that's because a lot of these original elements, their names were either in Greek or Latin or in some other language. And so what we did is we went ahead and kept the original name and used the symbol of that name, even though we don't use it today. All right. We'll talk more of that on later time. All right, compounds. A compound is another pure substance. So what exactly is a compound? Well, it is made up of two or more elements that are found in fixed ratios and cannot be broken down into be broken down into simpler substances such as elements. So in other words, when we take elements and we combine them together in fixed ratios, then we create compounds. What we mean by a fixed ratio is that there's a certain number of elements compared to other elements in that compound. So for instance, you know from experience that water is made up of hydrogen and oxygen, and it comes in a fixed ratio of H2O. H2O. So there are two hydrogens to one oxygen, and so that's a fixed ratio. So no matter where you go in the world or the universe, water always has a 2-to-1 ratio. All right. This, by the way, is called a chemical formula for the compound. Chemical formula. For instance, copper oxide has the chemical formula of CuO. All right. Copper symbol is Cu and oxygen is O. All right. So there's a ratio between those two, and that is a 1-to-1 ratio. So there's 1 copper to 1 oxygen. We don't usually put the ones in the formula, but you can see that it's a 1-to-1 ratio. So we'll look at some more ratios in just a minute. All right. Now, because elements, compounds are so small, we cannot see them with our eyes. So chemists, they're going to often build what we call models. Oops, I want to highlight that. Models. And these models are used to represent elements and compounds that make up different material. Now, models are only a representation, all right? Representation of what we believe matter is like and how it behaves based on observations and experimental data. So I want you to understand that. Models are based on observations and experimental data. Therefore, ultimately, models are just theories. All right? And that's something you need to know. Models are theories that try to explain the behavior of matter. Scientific models are often modified to fit new experimental data. All right? So throughout the year, you're going to see this. We're going to learn about different scientific models, and we're going to see that over time, some of these models have had to change a little bit in order to fit the new experimental data. So in this class, you'll need to become familiar with some of these models and how they work. All right, so here's some models that we have made to represent different compounds, such as a model for oxygen, water, carbon dioxide, ethanol, which is alcohol, and ethylene glycol, which is another alcohol, and then aspirin, which is a painkiller and you're familiar with. These models have been built because this is what scientists believe is the structure of these compounds. You don't have to memorize these structures or these models, but I want you to get a feel that throughout the year you're going to build models. We're going to look at models of how we structure elements together to form these particular compounds. All right. Now I want to go back and look at these ratios really quick, as I mentioned before. So oxygen, by the way, in a model like this, red represents oxygen, white represents a hydrogen element, black represents a carbon element. All right. So oxygen is made up of 2 oxygen elements, and so we would write out a formula of O2. Water, we just looked at earlier, is made up of 1 oxygen and 2 hydrogens, so it has H2O. Carbon dioxide is made out of 2 elements that are oxygen and 1 carbon, so it has a formula of CO2. Notice it has a fixed ratio, 2 oxygens to 1 carbon. All right. Now ethanol, we'll write that out. Ethanol, if you count up, you will see that there are 2 carbons, two black models there to represent carbon atoms. So we go 2 carbons, C2. There are 1 oxygen, and how many hydrogens? There's 1, 2, 3, 4, 5. So we're going to go CH5, and then the 1 oxygen, O. Okay? So the ratio is 2 to 5 to 1. All right? Ethylene glycol, what's it? It has 2 carbons, and it has how many hydrogens? 1, 2, 3, 4, 5. And then it has 2 oxygens. So C2H5, and then I'm going to squeeze in the O2. All right, for the ratio of C2H5O2. All right, and then you can do the same thing with aspirin. You can count out the number of carbon elements, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. So it would be C9. And then how many hydrogens? 1, 2, 3, 4, 5, 6, 7. There's some behind here and so forth. But anyway, you get the idea, and you can represent these models with chemical formulas. All right, now we're going to turn our attention to mixtures. So we just looked at pure substances, which are elements and compounds, and now mixtures. By definition, a mixture is made up of 2 or more pure substances that do not react with each other. All right, so we take pure substances, elements and compounds, we put them together, but they do not interact or react with each other, and therefore we have a mixture. Now, the first type of mixture we're going to look at is a heterogeneous mixture. By definition, a heterogeneous mixture is one that is not uniform. That means it varies in its composition and or properties from one part of the mixture to another. A mixture of rocks and water is a great example of a heterogeneous mixture. So when you look at rocks and you look at water together, you notice that they are mixed together because they're in contact, but they don't react with each other. And they're not uniform. They don't look the same throughout. Here are some examples, like different colors of M&Ms. That's a heterogeneous mixture. They're all mixed together, but they don't chemically react with each other, nor do they look the same. There's definitely variations in their color. We also have a mixture of different candies here. Again, it's a heterogeneous mixture. It does not look the same throughout the whole mixture. And then we have rocks. Rocks are a mixture of different compounds or elements that do not react with each other. And you can kind of see the different colors in this rock here. And therefore, the rock doesn't look uniform. It doesn't look the same throughout the entire thing. Okay? What about homogeneous mixtures? Well, homogeneous mixture is uniform. It has the same composition and properties throughout. A good example of that is salt, sodium chloride, and water mixed together. So when we take salt and we add water to it, we create a uniform mixture that is homogeneous. Kool-Aid here is another example of a homogeneous mixture. We add Kool-Aid, which is mainly sugar, and water. They mix together and they form a uniform mixture. Notice that Kool-Aid has the same color throughout the entire mixture. So that is what makes it heterogeneous. Now, another homogeneous, I said, so Kool-Aid is homogeneous. So another word that we use for homogeneous mixture is a solution. Now, a solution is a very special type of homogeneous or homogeneous mixture, and that is we take two or more substances which may be solids or liquids or gases, and then we combine these together. Now, there are two component parts to a solution: the solvent and the solute. All right. Now, the solvent is usually the part of the solution that has the greatest quantity amount. All right. The solute is the substance that is dissolved in the solvent, so it gets dissolved. So I need you to know the difference between the solute and the solvent in a solution mixture. All right, so here's kind of a beaker here. Let's kind of give you an example of a solution. We're going to make one. So we're going to put in a solvent here. And so the solvent goes in first, and then we're going to take a solute. Our box is going to represent some kind of pure substance, and we're going to add it to the solvent. So this is the okay, and so when we add the solute to the solvent, it will result in a uniform mixture. So a uniform mixture. All right, throughout. And so that's simply a solution. Okay. All right, so this is all for this lecture video. Make sure that you have taken really good notes, study your notes really well, and prepare for the quiz over this lecture video. And that is it for now.